Okay, well, hello everybody. Welcome back to MI212. Mark Gastonga here, and this is our lab session for the topic on parameter identifiability, nonlinear PK, time-dependent PK models, and target-mediated pharmacokinetics. So these, as you know, these are more advanced PK modeling topics, but they all have a similar theme in that we're using the differential equation block and numerically integrating these models using one of the various solver methods available in a tool like NONMEM. So the examples this week are pretty straightforward. Since we have the exam this week, all I really wanted you to do was to look at the code and execute the models, and let me know if you have any questions on those. We'll run through them in class today, and then I think we'll also take a little bit of time to review some of the study guide questions on this topic. One last reminder that the exam closes tonight. So at 12:05 a.m. tomorrow morning, you won't be able to get into the exam anymore, so please do complete it before then. Most of you have done so, and the grades look pretty good. Okay, so, well, before we dig into the examples, I had posted a polling question, and about 75% of you had voted on this. The question was, which are strategies for dealing with a priori identifiability problems? And the potential answers, and you were to pick as many as were appropriate here. The potential answers were: 1, use a different maximum likelihood estimation method. That's not the correct answer. Maximum likelihood estimation methods are not going to help you with a priori identifiability problems. So that was not to be selected. The second option was to collect data from an additional sampling site or a different route. And of course, we've identified that is one potential solution if you're selecting from a sample site or route of administration that now makes that parameter identifiable. Simplifying the model, of course, that's always an option and would help in that case. Fixing model parameters would be required if you don't have data sampled from one of the required sampling pools or routes of administration. You'd have to revert to some prior knowledge and fix them. And so that's also correct. And then the last choice, use informative prior distributions and Bayesian analysis. And that, of course, is also correct. That's almost analogous to fixing model parameters, except that we're not fixing the parameter at a particular point estimate, but we use a distribution and maybe an informative prior distribution to anchor that parameter. So all of the last 4 of those options were possible answers. The first one was wrong, though. And I think most of you did select those 4. Good job. Okay, let's turn on the broadcast here, and I'll show you the examples. And so you should all see my screen now. What I've opened up is the CIMI interface. And the zip file we provided, if you unzipped it in the MI212 folder under your home directory, should have created a directory called advpk1. And then there's a subdirectory structure there. There's one called examples. And then we have a separate directory for each of the topics that we were going to discuss. So let's start with a nonlinear clearance model. This is the first one we discussed in the lecture. To review here, we'll look at the control stream first. This is a model that incorporates both linear and nonlinear clearance. So it's a parallel clearance model, one that's often used in modeling PK of therapeutic monoclonal antibodies. It's useful in those cases where the concentration range is one that covers both the saturable target mediated type component of the disposition, as well as extending beyond that to the more linear pharmacokinetic elimination. So, usual stuff here at the top. We've got $prob, the listing of the problem. We have input items in the data set, and you've probably seen the data set, but it's just a pretty straightforward pharmacokinetic data set with ID, time, amount, a constant rate infusion, dependent variable, event ID, a grouping factor, and then weight. And then we also have the data set defined here. We're ignoring any row that begins with C. We're going to use Advan 6. Trans 1 is the default for Advan 6. Advan 6 uses a Runge-Kutta numerical integrator. And tolerance is set to 8 here. This is something you might initially start with arbitrarily, but through some trial and error, you'll determine how precise you need that numerical integration to be. Remember, the higher the tolerance, the smaller the numerical integration step size. The new control stream record that we talked about was the model statement. So how many required parameters in the model? There are 10. There are 2 compartments. And the names of the compartments here are just listed comp equals, and then anything to the right-hand side of that would define the name of the first compartment. It's the central, and it's also default for observation and dosing. And then you have the peripheral compartment. It's not necessary to specify the default behavior with regard to dosing and observations, because the CMT data item will override this anyway. But in this example, we did not require a CMT data item. So if in the absence of the CMT data item, you do need to specify where the default dosing and observations would be. Okay, so this is a dual mechanism elimination model. In $PK, then we're going to have to describe both of those mechanisms. We have a typical value of Vmax for the nonlinear component, and we've made that Vmax dependent upon weight. Normalized here, it's probably the median of the population, 72 kilograms. There's an inter-individual random effect on Vmax as well. We define a Km. Here we've just specified a population typical value, no inter-individual random effect, and that's usually the best you're going to be able to do in these types of models, unless you have a wide range of doses and concentrations within each subject. Otherwise, you're really just borrowing across the population to understand that inter-individual variability in the capacity on the nonlinear system, and oftentimes you have to collapse it down to a single random effect. You'll see that too. If you try to estimate both of these, you may lead to convergence problems. You'll also see a high correlation in the inter-individual random effects between these two parameters. Then we define the typical value of clearance, the linear clearance, CLL. Again, that's going to be dependent upon weight and has both fixed and random effect components. And similarly with central and peripheral volumes. The intercompartmental clearance here we've left without any inter-individual random effect or covariate effect. And that's usually because it's difficult to identify that, although sometimes it does lead to more stability if you specify covariate effect there, even if you can't estimate an inter-individual random effect. And that's just because all of the other parameters, the volumes for which the intercompartmental rate constants will be derived, are weight normalized, and so we might want to do the same thing with Q, although maybe it didn't support it in this case. Could be something that you want to go back and try. Okay, S1 is V1. That's just our scaling compartment, identifies where our observations are occurring. Let's get down to the real nuts and bolts here in $DES. This is where we specify the model. And what we're doing in this case here is writing our equations in terms of a DC dt, or a concentration change over time. And in order to do that, we're going to define the concentration in each compartment. So C1 is equal to A1 divided by the volume for that compartment. Remember, A1 in parentheses is a recognized variable in NONMEM. It always represents the amount in a particular compartment specified in the parentheses. C2 is likewise A2 divided by V2. So for our first compartment, this is an IV input, so we don't have to worry about initial conditions. That's determined by the data set. So we're just talking about the change in that concentration time relationship over time. So the rate of change here is defined by a loss attributed to the saturable component, so minus Vmax times concentration divided by Km plus concentration. That's the saturable component. We also have minus linear clearance times concentration, right? Then minus the peripheral distributional clearance, and then of course taking back what's coming from the peripheral compartment. So we have a rate of change expressed in the two elimination mechanisms and then the distribution impact on that first compartment. The second compartment is really just a distribution impact there. So you've got flux coming in from the central compartment or compartment 1 and then exiting from compartment 2. So pretty simple system. We just have the complexity of the dual elimination mechanism. Since we have only a single compartment to make observations in, and we've defined the default observation, when we specify F in the error block, we're going to get the prediction for the compartment that we're interested in. So the default observation is compartment 1, and so F will be set to the prediction for that default compartment. If we had not specified a default observation, then we'd need to be more specific here in the error block, and we might want to say something like this, C1. Again, we can repeat what's in the DES block. And in fact, you do have to repeat variables if they're described in the DES block. It doesn't mean that they'll be accessible to you in other parts of the code. So we can define the same thing here, and then or just to be clear, maybe we wanted to change the name, and we just change F to CP. This would work in the current implementation as well, but it would be required if you if you had not specified a default observation compartment in the $model section. Remember up here. Okay. And it's also very useful if then we're going to have multivariate endpoints where we have observations in different compartments. Then you need to get specific about which compartment is which. And it's very useful to be explicit about that, like I've done here. Okay, other than that, then we've got initial estimates for all the parameters. We have some initial estimates for the covariate effective weight. The omega here is a diagonal to start, where we have inter-individual random effects on Vmax, linear clearance, and central volume. Sigma is just a single exponential error term. And I think I'm not sure in your example, I've coded this so we're running method 0. Method 0 is the first order method. Ideally for these models, you probably want to use FOCE or FOCE interaction if there's a proportional component of the residual error model. But for the purpose of running in this class, I'm going to use FO. Okay, so we can save. In fact, let's try this here. We hadn't constructed it this way, but I'm going to put the weight effect on Q here, see what happens. And we just have to add that to our initials. Q is a function of weight. Okay. So I'll save that. And let's look at our R script for this run. So in the nonlinear clearance directory, so you can see here when examples nonlinear clearance, there's an R script. Let's go edit that R script. And the usual stuff here, we've got to load libraries and set up project directories. So what I'm going to do here is open an R window next to this window. Okay, and I'm going to look back to editing now. So I've already been running here, and let me just double check that it's there. Yeah, so our library is loaded. We're all set to go. Project directory needs to be set here because I was running a few different examples. So let's set the project directory. And then we're going to just use the non-R function to call NONMEM. We're going to set a single run here, run 1. Our NONMEM run command is the same that we're always using. Project directories defined above. We are going to then define continuous covariates, maybe some parameters we'd like to plot, a list of ADAs. We're always using grid true, and we're going to plot diagnostics here too. Okay, so we execute this function. And again, the run is submitted in terms of a compile and execute. And yeah, somebody just points out that I forgot to change my user directory here. So it just so happens that there is a NATED directory on this server, so it's going to still run, but our results won't be there. So we'll set that again. In fact, I can do that now. Okay, well, let's rerun so that the results are in my directory now. Okay, I'll answer a few questions while this is running. How do you determine appropriate initial estimates for the nonlinear PK model? Yeah, that's difficult to do sometimes. Of course, we can get estimates of clearance. What you can do is if you have some non-compartmental results or maybe just some average concentration data, and you know the rate of input across dosing groups, you could get a rough estimate of clearance that way by dose group. And then you can see, where the clearance is changing versus where is clearance consistent across dose groups. That might help you to discern the linear estimate versus the nonlinear. Andreas also says, go ahead and use something like WinNonlinear Berkeley Madonna to explore. So plug in different values and see what it takes to make the equation, make the model fit the data. And that's true. You can also do that in NONMEM by just running maxeval 0 at a variety of initial estimates. But tools, especially like Berkeley Madonna, which has a nice graphical interface with the slider that allows you to quickly explore a range of parameters. But if you want a ballpark, you can get some pretty quick estimates to the clearance range. Okay, run 1 is completed. Yeah, a comment here. I didn't change the number of required parameters, but that's the number of required parameters. You could have extra parameters. So npar equals 10. I don't have to change that to npar equal to 11. And in fact, that npar variable is completely optional. You can specify the parameters as you'd like. So let's go to the results here. A bit of refresh. So here's the model I just ran with the weight coefficient in there. Let's see what happened. So minimization was successful. We'll look at the gradients here to see if there's any problems. First of all, the first thing you want to look for is zero gradients. I don't see any zero gradients throughout the process here, so that's good. And then we'll also make sure that the gradients are well behaved, going from a large, relatively speaking, absolute value to smaller absolute value. And that looks decent there too. Parameter estimates are listed here. And I forget the order that we had. But we had Vmax, Km, clearance, volume, and Q. So Vmax is 0.8. Was it Km or clearance? No, I forget. I think Km was 7.9. So that's your concentration that produces half maximal velocity. And then we had also the linear clearance here, which is kind of small. Yep. We've got, and so on. So you have parameter estimates here for the fixed effects, the covariate fixed effects as well, the inter-individual covariance matrix, which is diagonal here, and the residual error. And we had the covariance step execute as well. So pretty stable looking run there. Let's look at the diagnostic plots. So population predicted versus observed on the left side and individual on the right. You see the heteroscedastic nature of the data, but overall a pretty unbiased fit. Looks good. Again, the residuals versus pred show you that heteroscedastic data, although conditional weighted residuals or weighted residuals show that that's been adjusted by the proportional model, so validating our choice of the proportional residual. Residuals versus time, we don't seem to have any bias over time here in this particular experiment. And QQ norm plots here for the really what we're modeling is a conditional weighted residual. Actually, we're using weighted residuals here because it's FO, but not too far from our assumption here of normality. The residuals, of course, are skewed, but that's not what that's because of the heteroscedastic nature. What we're really concerned about is that the weighted residuals are normal. And in this case, both the weighted residuals and the conditional weighted residuals are quite similar. In fact, if we didn't run post hoc, they're going to be the same. So that's why. QQ plot here, yeah, they're the same. So we did not run post hoc. Yeah, we did. Okay. The eta scatter plots then. Not a great deal of correlation, although eta 2 and 3 might have something there that might justify including a block. Parameter scatters, that just shows you the relationship between those. The histograms of the etas looks okay. Maybe eta 3 here is a little off. The density plots will give you a little more clarity there. But it's a small data set, so not so bad. And then we're looking at continuous covariate effects, and so effects versus weight. And then the conditional weighted residuals here as a function of weight. Looks good. So this is overall a pretty good fit. Of course, it's from simulated data, but just about what you'd expect. So let me just answer a few more questions, and we'll look at the next example. Yeah, somebody's asking about the software that Andreas mentioned. The useful tool is called Berkeley Madonna. It's not free, but it's available for a nominal fee. It's a handy tool to use. It does least squares estimation of individual level data, but it also does quick simulations too. And there's a graphical interface to the model specification language that allows you to explore the impact of changing parameters. Andreas corrects me here and says there is a free version, and there's very few functionality that's not there in the free version. Didn't know that. We had actually, anyway, it's not expensive even if you buy the licensed version. Next question here is about what about the gradient checking? What kinds of signs are we looking for? Well, we talked about this extensively in the last class, the 210 course. But remember, we're using gradient-based methods that should be decreasing the gradient as the search progresses from iteration to iteration. So the absolute value of that gradient should be going from some large number to a smaller number closer to zero. That's because our search is making large, steep steps initially, and then as we approach the global minimum, the step size and the change of the objective function with respect to the parameters becomes much more shallow. The other thing that we want to look for is if there's a zero gradient. So if there's a zero gradient from start to finish in an estimation problem, that is indicative of a parameter that has no impact on the objective function. Usually it's indicative of a coding problem or a data set problem where that parameter is not impacting the model at all. So a zero gradient is something that's a red flag anytime you see it. Now, zero gradient from start to finish is certainly problematic. It's also possible to see a solution flip to a point where the gradient is zero at one of the iterations. And that's probably indicating a parameter that's having difficulty, poorly defined, maybe an identifiability problem. Okay, so that's what we're looking for with respect to gradients. Well, let's go to the next example. Next example here is the time-dependent model. And again, let's look at the control stream first. All right, we'll edit 1.ctl. And by the way, when you see here in the example folder, I'll post these solutions as well. There's a run 1 and there's a run 10. Run 10 is actually the simulation code that was used to generate the data set that's used in the estimation run that we're running under Model 1. So just in case you want some insight as to how you would simulate that data set, we've given you the simulation code there too. Okay, so here's 1.ctl, and I already had it open. Let's see. So this is a clearance auto-induction model. We talked about this one in class. In this model, we're imagining that because of administration of this drug, there's some change in metabolic enzymes, an induction of enzymatic expression. And we're going to model clearance as a clearance that starts at some baseline value and increases with an exponential asymptote to a maximum clearance over time. There's lots of different ways you could imagine this model or propose it, but this is one way. The data set is very similar to what we just talked about. We're going to have IV input here. The model has one compartment. So it's a real simple model. One compartment model with a time-dependent clearance. It's the default dose and observation compartment. Of course, it's the only compartment. So let's get right down to the differential equations. You see that clearance is defined in the differential equation block, and the reason we're doing this here is because we want to take advantage of this very handy variable t. T is the integration time. It's an approximately continuous measure of time, which is to contrast that from time in your data set. Remember, time in your data set only changes at the times that you have data records. So if you have large gaps in time in your data records, any function of that variable time, TIME, will be a step function that doesn't change any more frequently than time changes in your data set. If you want a parameter to change as a continuous function of time, you use the variable t in the differential equation block. So that's what we're taking advantage of here. Clearance is going to be equal to some baseline clearance plus some maximum change here, which is approached with this asymptotically exponential increase according to some half-life for that rate constant. Concentration in compartment 1 again is defined as A1 divided by V1. So this dAdt here is actually a dCdt, modeling a change in concentration versus time, and it's going to be equal to minus clearance, which is defined by this time-dependent function, times C1. Pretty simple, pretty straightforward. Again, F is used here. F is going to take on the prediction for the default observation compartment. So that one's pretty straightforward. Parameters to be estimated are the usual ones. We can run it here in class. It's a short run, but I'm going to use method 0, the FO method, just to be clear and just to make sure that we have time to complete it. And I'm going to include the post hoc step. Oops, I need caps. Okay, so let's save that one. And the R script is here called time-dependent clearance.r. Let me open our R window as well. And the library is already loaded. We'll change the project path. Don't want to use caps there because this is a case-sensitive operating system. So we'll save that. We'll evaluate the project directory. And now we're going to run non-R. Again, very similar setup as before. The same types of options. Parameter list, ADA lists are here. Grid true, that's what we'll always use in this class. And diagnostics will be plotted too. So that's that run is on its way. While that's running, let me answer a few more questions. Sorry, I lost my mouse here. Somebody's asking about a DS store file. Some of these hidden files are really inconsequential. They're part of the Mac OS operating system. You could ignore them. They're just part of the file structure. Any mechanistic basis for this clearance function? What we're doing here is very much a description of the data with some mathematical function. It doesn't necessarily have a mechanistic basis. If you wanted a more mechanistic model, you might try to look at this as some sort of an indirect response where there might be an increase in production of expressed enzyme. So you could have something like an indirect response model with a drug that potentiates K-syn, and then that amount in that compartment could modulate clearance. That's one way to do it with a more mechanistically inclined model. However, this simple description probably works quite well. The one caveat to this one here is that if you happen to stop administration of the drug, so there's a drug holiday or something, there's no mechanism here for this autoinduction model to return to baseline. It's just going to continue to maximize to an induced clearance over time. So this is assuming that we're having chronic therapy here that's continuing over time. Yeah, somebody is asking if you can execute the next run before the previous one is complete. You can do that in a semi. those will be separate commands, and they're running as separate command line calls. Let's see what happens. Looks like we've completed this run. We'll go back now. We're going to work on time-dependent clearance. We get diagnostic plots to look at. So there's the model on the left-hand side for the observed and population predicted. On the right-hand side, it's for the individual prediction. You know, one interesting might be for you to go back and try this model with a constant clearance and see what happens. What you'll see is that there should be some bias over time. The residuals versus time gives you a view of the variability in the data. Weighted residuals are nicely balanced, as well as conditional weighted residuals. There's no trend over time here, which is where you might see some bias in this model if you used a stationary clearance. Weighted residuals and conditional weighted residuals all look good. And so, and of course, since we ran the post hoc step and we're running FOB, these are similar. Eta scatter plots don't show any strong correlations here, but you could explore an omega block. And then I like the density plots better here. You know, for a small population, I wouldn't worry too much about these eta distributions. Again, we could explore this further through simulation-based diagnostics in a predictive check of some quantity of interest. But overall, it looks like a pretty decent model fit. What you might want to try to do is to go back and run that with a stationary clearance. You know, in fact, we might have enough time to do that here, so I'm going to illustrate that. Let's go back to 1.ctl. And I'm going to change that to 2, just for comparison's sake. And refresh. So 2.ctl. We'll call this a constant clearance model. And it really simplifies our model here in that we don't need all of these parameters. All we need is a parameter called clearance. We don't need clearance max. We don't need half-life. We do need a volume, so make that theta 2, and eta 2. So let's really simplify this model now. This entire specification in the differential equation block is unnecessary, so that dAdt is just minus clearance times concentration. Concentration in compartment 1 is amount, and 1 divided by volume. That's all correct. Let's change our initial estimates here. We can drop these guys. Oops. Okay, so we've basically eliminated the time dependency here. We now have a constant clearance and a volume and distribution, which is also constant. We'll have to drop this interindividual random effect too, so I'll comment that line out. So we have a clearance random effect and a volume random effect. The rest is the same. The other thing I need to do is clean up my table file here. So clearance, get rid of these guys. And eta 1 and eta 2. This is a function that's automatic in MIfuns, which changes all your run numbers. I'm just doing it here to illustrate that these are changing. Okay, so I think we've got all the changes we need there. We still have the same number of compartments. Parameters, I'm just going to drop at par. Okay, save that. Let's go to the R code for time-dependent clearance, and all I'm going to do now is copy this run, and we'll call it run 2 now. Our parameter list is simpler. We don't have we just have clearance and volume, and we just have eta 1 and eta 2. Get rid of that comma. Okay, save, and now let's execute this run. So that's been submitted and compiling, now executing. Okay, let's see what happens. We'll go back to the questions here. Okay, no new questions, so we'll just wait a minute here for this run to complete. Looks like it's complete now. Let's back up. Time dependent. Here's run 2, and we can look at the list file. So this was successful, quick run. Just a few iterations. The gradients, we don't have any zero gradients here, so that's a good diagnostic. The magnitude is decreasing for each one of these. Good shape. And so we've got an estimate of a constant clearance of 8.29 liters per hour and a volume of 31 liters. Inter-individual random effects are larger than before, in case you didn't notice that. And I imagine the residual would be too. Objective function for this run is 1228. Let's look at diagnostic plots. So you see some proportional variability. Use the whole screen. Although it doesn't seem too biased over that range. When we look at residuals versus predicted and weighted residuals versus predicted, not too bad. A little bit of a dip here in the residuals. And then you see a bit of a time-dependent trend where initially positive residuals and later on negative residuals. That's accentuated even more when you adjust for weighting. So this is the kind of thing that indicates the potential bias in the time dependency. And this is where you would pick up the need for that time-dependent clearance. So you can go back, you can compare objective function and parameters in more detail, but you see from these plots right here that there is that trend towards a time-dependent bias. And of course, if you study the experiment longer, or if it takes longer to reach the maximum clearance, the more data you have, the more apparent that bias will be. All right, so that's the time-dependent model. And last, we'll talk about the TMDD model, the target-mediated drug disposition. Let's look at the control stream. And I'm not going to run this one in class because it's a long runtime, or about half an hour or so with FOCE. I'm not sure what we've got with FO. You can run this on your own. I'll just review the results with you. The control stream here, and what we've done here too to make this clearer, it's slightly different than what we had written in your handout. We converted everything. All compartments are concentration time, rate of change, and all of the units now have been converted to molar concentrations. This is really what you need to do when you have free drug plus a target and a drug target complex. In order to make those compatible, you've got to use units that allow you to match those up. So we're using molar concentrations. You need, of course, molecular weights for the drug and the target. But that's usually a pretty straightforward calculation to make. So this model, we have 3 compartments: central, a target, a complex, and then the peripheral compartment for drug. Again, the observations our default, or the default dosing is central. Default observation is central too if you had only a central compartment observation. But you'll notice we have a CMT data item here, which overrides anything we set up in $model. We should probably take a look at the data set. The data set actually contains data in all three of those pools. So we have observed free drug, we have observed target, and we have observed complex. So when you have all of those compartments, this is definitely an identifiable system, and it simplifies estimation. But the data set has to indicate then that we have those observations in specific compartments. Okay. So now we have a PK block where we define different components of the model. First, clearance, central volume, intercompartmental clearance, and peripheral volume. That's the free drug PK model. We have microconstants defined here because remember, advan, all of the differential equation advans use a trans 1 assumption that's microconstants. So we're going to define the microconstants here for that relationship. The base here is a baseline concentration of free target. We have this is sort of a little bit out of order. K int is the internalization or the elimination rate constant for the complex. K deg is the elimination rate constant first order for the free target. K on and off are the binding rate constants. And K sin is a zero order constant rate formation of free target. We're going to use the initialization trick in the control stream here where we can initialize compartment 2, so A underscore 0, or the initial conditions for compartment 2 are set equal to this baseline parameter. So it's an estimated baseline. Although we may have observed values at time 0, there's some residual error in those observed values, and so we're going to just use the estimated baseline as the initial condition. Differential equation block here specifies the concentrations in compartment 1 and compartment 4. And then we simply specify the rate of change equations now, which are dCdt, the way we've written it now, concentration time equations. So you have the PK system, elimination from that compartment. We have the K on, this is the second order rate constant for binding between free drug and free target. We have then the K off times A3, which is going to dissociate the complex back into its individual components of free drug and target. And then we have the minus K12, that's the transfer to the peripheral compartment, and then the return from the peripheral compartment. For the free target, compartment 2, we have K sin, which is our zero order production. You'll notice it's not multiplied by any concentration here because it's zero order. K deg, which is first order degradation of the free target. Then we have that second order rate constant K on times the free target times free drug, plus then the dissociation K off times the complex concentration. DADT3 is the rate of change for the complex, and of course that's just the K on times free target times free drug minus the two elimination sources, which are K off times complex and K internalization or the elimination of the complex times A3. And then compartment 4 is just your peripheral PK compartment. So all of this is pretty, as long as you pay attention to the details here, it's pretty straightforward. It can be derived from the differential equations or even from the schematic diagram that we had constructed. The tricky part here now comes when we're making predictions for different compartments. So now we have observations in all three pools, and so we're going to describe the prediction for drug. We'll call that F drug. That's the free drug. The prediction for free target is A2, and the prediction for the free complex, or not the free complex, but the prediction for complex is A3. We use an indicator variable then to switch the prediction according to all of these. And then we're also going to allow for a different residual variance model for each endpoint. And that makes sense because you're going to have different analytical assays or different methods to determine the bioanalysis of those analytes. And they may have different precision, different residual variance. So we're going to try to estimate that. And then we have initial estimates for the model parameters. Again, this is a place where it is helpful to use a graphical tool to explore different parameter values, but you can also potentially borrow from some prior knowledge, maybe some in vitro understanding. And inter-individual random effects now, we're going to keep it simple, only 3 parameters, and that's probably a good place to start for these kinds of models. Just keep it simple to get going. We have 3 proportional residual variance terms, 1 for each of the different analytes, and this one's going to be run with FOCE. We could actually run FOCE interaction here because you do have a proportional residual random effect. The interaction would be helpful in that it allows the individual specific prediction to be part of the weighting of each data point rather than relying on the population level. But that's the basic idea. There's a couple of interesting things in the non-R call for you to take a look at. And this is a general implementation of an option when you have a multivariate endpoint or more than one dependent variable. We're going to run NONMEM as usual, but we've got this new option that we're using here called group equals CMT. So this is the variable in your data set that allows for separation in the different analytes. It's an indicator variable, and it just so happens that it's the CMT item in this data set. And then if you'd like, you can specify according to the different levels of group, you can give them different names. So we'll call them free drug, free target, and then the drug target complex. The rest of these things are the same as usual. What this will do now, though, is we'll split up our diagnostic plots according to the different types of analytes. So let's take a look at what happens there. Here's the diagnostic plots for this run. And what you're going to see then is 3 batches of diagnostic plots. This first one here is for free drug data, and we see the observed versus population and individual predicted. Not a lot of data here. But that was a small data set just for keeping the runtime short. Looks like a pretty decent fit for free drug. Residuals, weighted residuals, and conditional weighted residuals you see in the next frame. These were done under FOCE. And you see that a couple of large weighted residuals, but those go away when you use the more appropriate CW-res, which is the value used under FOCE. Again, versus time, it looks like pretty consistent over time. No major trends there. So it looks pretty good. Now we're going to look at one more plot, the QQ plot. Conditional weighted residuals are very nicely distributed according to that normal theoretical distribution. And this plot here is one that we will do conditional weighted residuals versus weighted residuals. This is one that would be useful in determining whether or not the FO assumption is useful for your data. If these two have a high degree of concordance in their distribution, it's usually evidence that the FO approximation is probably okay for your data set. Here you see it's not okay because of this skewness in the comparison of the quantiles of the conditional weighted residuals versus the weighted residuals. Okay, now next we're going to look at free target. Again, the same sorts of things here. It looks pretty good. You see heteroscedastic variability in the observed data. versus prediction, trends look pretty good. Again, versus time also looks decent. Conditional weighted residuals are close to where they should be. So this is a model where you might run FO for simplicity and the brevity of the runtime, but really this diagnostic is telling us you need to run conditional estimation here. And then finally, the drug target complex data. So we have observed data there, and again, population individual diagnostic plots. You see the heteroscedastic variability in the data. Lots of points here at low predictions, and that's because it may be because we have a rapid K internalization in this system, but relatively unbiased across the range. Same sort of thing over time. And again, comparing the residuals, weighted residuals, and conditional weighted residuals to the standard normal. Conditional weighted residuals are right on. Weighted residuals are a bit off, although not too bad, but again, indicating that conditional estimation is probably necessary for this model. Eta scatter plots show us here the random effects are pretty much independent, although you could probably try to model an omega matrix and see what happens. I always go with the philosophy of attempting the most complete omega matrix that the data will support, regardless of what those plots look like. And eta distributions, a little bit of skewness here, but remember, we're dealing with small counts, small numbers. Looks okay. So anyway, that illustrates not only the diagnostics for this model, but how we can use the non-R function to call for diagnostic plots that are categorized by different analyte values. Okay, let's switch over to a couple of questions. Do we really need all three types of data to identify a TMDD model? Yeah, this is a very good question. What if we just have total receptor and free drug? You can try to run this, and so I don't think there's been a thorough analysis of the a priori identifiability of this system. I think certainly if you have all three, we can be confident that it is a priori identifiable. What's been shown is that when you try to run this model and you have only free drug, that there are identifiability problems, and we probably just know ahead of time that the system will not be a priori identifiable. It might be locally identifiable with a couple of solutions, but as far as I know, there hasn't been a rigorous evaluation of the a priori identifiability of this model. Can you get by with just free drug and total receptor? Maybe. There still have been some examples, simulation-based examples that have indicated that there are still identifiability problems there. Whether it's a priori or a posteriori remains to be seen. But certainly, if you just have free drug, this is not an identifiable system. The question about did we use concentration time or amount time? I think we used concentration time for the rate of change here throughout. So everything is concentration based in this particular example. We're assuming we have measured things in concentration. And we're using molar equivalents here. Okay, we're almost out of time here. I just wanted to point you back to the study guide questions for this chapter. Remember, this is the kind of topic that we think is important and will probably be the substance for the next exam. But remember, understanding the difference between a priori and a posteriori identifiability, that's important. Local and global identifiability, again, two important concepts. We talked about strategies for dealing with identifiability problems in the polling question at the beginning of class. thinking about some of the mechanisms for underlying nonlinearities or time-dependent PK, and then understanding some of the assumptions made in the quasi-TMDD models, either the quasi-equilibrium or the quasi-steady-state implementations. There's lots of literature on this. This is still an evolving science, and it's probably worthwhile to keep your eyes on the literature in this topic area if it's something you're working in, because there have been continued developments in reparameterizations of these models or specification of identifiability or prior information to support estimation of these models. So keep your eye out on the literature in this case. Okay, I think we're going to wrap up for today, and remind you again, those who have not taken the exam, please complete it by tonight. At midnight it will be closed, and all grades will be final at that point. We also have a new topic next week. We're going to talk about models for parent-metabolite PK data, and as well as incorporating plasma and urine data. There's an article for you to read there that addresses some of that. Besides that, no more assignments until Tuesday. We'll talk again then, and we'll have a homework problem for you to work on next week too. Thanks for your attention, and we'll sign off for now.